Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. We had a date with a comet last night, and things went exceptionally well. We did have to wait a long time for those images to come down this morning, though, and that is why we are starting a little bit late, and please accept our apologies for that. So we are bringing you the latest images that are hitting the ground as we speak. Let me introduce the panelists for you now. First, we'll have Dr. Ed Weiler. He is NASA's Associate Administrator, the Science Mission Directorate at NASA headquarters. Tim Larson, the Stardust-NExT Project Manager from the Jet Propulsion Laboratory. Dr. Joe Veverka, the Stardust-NExT Principal Investigator from Cornell University in Ithaca, New York. Dr. Don Brownlee, the Stardust-NExT co-investigator from the University of Washington in Seattle. And Dr. Pete Schultz, another Stardust-NExT co-investigator, and he's from Brown University in Providence, Rhode Island. And we will begin with Dr. Weiler.
Thank you, Veronica. 5.5 years ago, a spacecraft named Deep Impact had a close encounter with a comet named Tempel 1. The mission was designed to drop off an 800-pound metal slug which would impact the comet at high velocity and throw up a bunch of comet material. The spacecraft's instruments would then look at that material and inject it to better understand the chemical makeup of these primordial bodies called comets. In fact, the principal scientist of that mission, Dr. Mike Ahern from University of Maryland, is in the audience today. But that was yesterday's news. In 2006, Dr. Joe Veverka from Cornell sent a proposal to NASA with a rather novel idea to retarget a different spacecraft called Stardust to revisit Tempel 1. Stardust is a 12-year-old spacecraft having completed its prime mission many years ago. This was the second time, actually, that NASA would take advantage of an old mission for new science and exploration. The first was Comet Hartley encounter with a reused Deep Impact spacecraft renamed Epoxy just last fall. Thanks to a great effort by the science team, engineers, navigators, Lockheed, JPL, and NASA, we are here today to show you the results of humanity's first revisit to a comet to study how these objects evolve over time. And I might add, the results you will see in a few minutes were achieved for less than 10% of the cost of a new Discovery class mission. Before I turn it over to Tim, I have a message for any school kids out there who might be wondering how NASA can send a spacecraft billions of miles through the solar system and somehow wind up flying so close to a tiny comet only a few kilometers in diameter. It's done with math. So pay attention in math class if you ever dreamed of being involved in this kind of real science discovery and exploration. Tim?
Thank you, Ed. Again, I'd like to reiterate this is exciting for us because it's the first time we've ever had the opportunity to visit a comet twice. If you roll the animation that we have, you'll see that Tempel 1 is a Jupiter-class comet that its orbit goes out as far as Jupiter, and in this case comes in as close to the Sun as the orbit of Mars. And that's about where we met it last night with the spacecraft. Based on the data that we brought down from the spacecraft, we've been able to confirm that our flyby distance from the comet was 178 kilometers, that's about 110 miles. We went past the comet at the velocity of 10.9 kilometers per second, which is on the order of 24,000 miles per hour. And our closest approach was right before 8:40 p.m. Here on the West Coast on Valentine's evening. Our spacecraft telemetry shows that all of our subsystems operating exactly as we expected during the flyby. The AutoNav software, which is the autopilot software that controls the motion of the mirror that keeps the comet in the in the field of view of the camera, worked exactly as planned and kept the comet exactly where it was supposed to be all the way through the flyby. All the desired data that we wanted to collect was all collected and stored on board. That's 72 images and approximately 3 megabytes of dust data for a total of about 78 megabytes of data. That doesn't sound like a lot to you, but this is an old spacecraft. The spacecraft is healthy. After the flyby, we were able to confirm that there is no noticeable degradation to the spacecraft, to the health or function of the spacecraft, despite the fact that we have detected several dust hits through the flyby, and you'll hear a little bit more about that later. So after the flyby, we turned the high gain antenna back to Earth and began to downlink our data as planned. At that point, since the spacecraft was healthy and we really wanted to gain a little bit more margin in our downlink to make sure that we protected this data and got it down in one pass safely, we decided to delay our downlink by about 45 minutes so that we could reconfigure both the spacecraft and the Deep Space Network Station to accommodate that. So that was accomplished, and that went very well. Next, we had our plan on the playback was to send 5 images that bracketed the closest approach period of the flyby. We wanted those 5 images to come down first in the queue when we started sending images back down to Earth. When we commanded that, it turns out, due to a software glitch that we had on board, the images started coming down in the order that they were taken. So this did not jeopardize any of the data that we had on board. All the data was safely stored in memory and was ready to be sent down. We just had to wait a little bit longer for those images that all of us were really ready to see at that time. So those images got down to the ground about between 6 and 7 o'clock this morning. You have already probably seen them out on the web, and some very exciting findings coming out of those. The spacecraft is continuing to send images down to Earth. At this point, we're approximately 60 out of the 72 images are down on the ground. We'll continue doing this until mid-afternoon. Once we've confirmed that all the images and all the data is on the ground and all the packets are complete, no corruption to any of the data that would require a retransmit, at that point we'll be able to reconfigure the spacecraft and get ready for our outbound imaging. When we do that, we'll spend 1 to 2 weeks at least of looking back at the comet as we go away from it, and as long as the scientists can get useful information out of that data, we'll continue that process. Joel, I'll leave it to you to tell us what we found.
All right. Well, let's see. Tim, a few minutes ago, said that he was excited. Let me just say, I mean, more excited. There is great science, and if we could have the first slide. This shows us selected 4 images taken around closest approach. And what I want to emphasize is that we achieved all of our science objectives. We had 4 major science objectives, 3 dealing with imaging, and 1 with the dust experiments that we have on board. The 3 imaging goals were, first of all, to look again at areas on Tempel that we had seen before in 2005 with deep impact, to, for the first time, see what changes occur on a comet when it comes close to the sun and where those changes occur. We also wanted to take the opportunity to look at the deep impact site where the deep impact impactor collided with the comet. And finally, we wanted to take the opportunity to extend our exploration and see areas on Tempel that we have not seen before. So we had 3 imaging objectives and 1 objective having to do with analyzing, collecting dust. Dr. Brownlee will talk about the dust, I'll talk about the imaging. And if you ask me, was this mission 100% successful in terms of the science? I would have to say no. It was 1,000% successful. And so I would like to just very quickly go over some of the highlights. What we're looking at here are 4 images around closest approach, and the way we planned this encounter was on the way in to see some of the old territory that we had seen before in 2005, including the deep impact crater site, and then on after closest approach to see new parts of the comet. So behind me here we have the approach images. I just point out 2 craters. This is the area where the deep impact impactor hit the comet. Up here, you can barely see in this image, is a region that was intriguing to us because we expected that region to change significantly in the 5.5 years between the encounters. So let me first of all show you one example of the changes in the next slide, which is that area that I pointed out before, the smooth area. This is a deep impact image. Up here, you see the region in 2005. This is about 2 or 3 kilometers in extent. This is maybe 300 or 400 meters across here. This is 2005. This is 2011. This is the current situation. And let me just point out a few things. For example, up here, you see 3 pits. Here you see 1 contiguous pit. erosion on a scale of 20, 30 meters of material has occurred in 5 or 6 years since we took this picture. Also, if you follow the outline of this boundary and compare it to what we see today, you will again see significant changes. So we were successful in that objective. We are seeing changes. We have to spend time quantifying those changes and understanding what they mean. Our second goal, if I could have the next slide. This is just shows us the two areas, the area outlined here where changes occurred and also the boundary. But what we're looking for is the following slide. And that is not the following slide, but how about the one, what have you got after that one? You have anything after this one?
Yep, that's the one they have for you.
There's no other slide.
Not at this time.
Okay, well then, folks, the way this is going to work is that we do, in fact, have a comparison of the deep impact area in 2005 and 2011, and it, in fact, does show an impact crater. Unfortunately, I can't show it to you, but Pete Schultz, in a few minutes, apparently, if we are lucky, he might actually have that comparison. So we were, again, successful. We achieved our objective. We not only imaged the area of the deep impact event, but we have an image of the crater that was produced. And finally, the slide that we have here is to exemplify our third goal, which was to extend the exploration of Tempel to areas we have not seen before. So this is a part of, in this picture, the parts that we have seen before are sort of behind, up here. And this is all new territory on the Comet, and it is simply amazing. There are extensive areas of layering, layers that have been deposited, each layer a few meters thick, maybe 10 meters thick. We have to puzzle, how did this happen? We have large regions, this is about 1 kilometer across, where material has apparently been sublimated from the surface and removed. There are areas on here which look like they're heavily pitted or heavily cratered. Geology that we did not see on the other face of Tempel. And to understand how this comet works, we have to put everything together. In closing, I want to emphasize that to achieve these three imaging objectives, we had to arrive at the comet at precisely the right time. As I mentioned, we planned it so that on approach, we would see the deep impact area, and then after closer approach, we would see new terrain. That meant arriving precisely at the right time, at the right place. And to achieve that, not only did we need first-class navigation, but we needed information on the rotation state of the comet. We had an international effort over several years of monitoring the comet's rotation and predicting what the state would be at encounter time. How well did we do? We got the longitude over which we wanted to fly to plus or minus 1 or 2 degrees out of 360 degrees. So that was a great achievement by our scientists. So we're tremendously happy, and I will now pass the discussion on to Dr. Schultz, who hopefully does have a picture of the crater.
Yeah, Joe, I sure hope I do. You know, I make craters for a living, but I've never had to wait 5.5 years to see the results. So if we have that first time step up there, and you can actually see what Deep Impact saw, and one of the close-up views that showed from the probe's perspective as it was zooming into the surface, and where it was going to hit 9P Tempel 1. If we go to the next time step, this is why we needed to go back. On the left-hand side is an image from one of the HRI images, and on the right is an image that Deep Impact saw about 700 seconds afterwards. You notice we can't see the crater. It's obscured by all the ejecta that was tossed up by the impact. We never saw the crater as we went by. It's there somewhere. That created a lot of mystery. It also helped to create this mission. Let's take a look at the next time step. And I just want to show you how well we can correlate the different features. On the left is an image from Deep Impact. On the right is Stardust-NExT. And you can see those two craters, those two crater-like features, each one of them about 300 meters across, almost 1,000 feet. Where we were aiming was right in between with deep impact. That's where that probe went in. And if we take a look at the next time step, which is not that, why don't we skip that time step? Huh?
That's a nice picture.
That's a nice picture, yeah. Very nice picture. I don't want to say.
Yeah, we're going to put that last one up.
Okay, is there another one after this?
No, there is not.
There is no. Hey, Joe, guess what?
It's clearly.
Well, no, let me just tell. Let me just tell
might
them.
have them by the end.
Hey, we saw the crater.
Yeah, really, we really did see the
We
crater.
saw the crater, and I tell you what, stay with me here, okay? We saw this crater. It's subdued. It's about 150 meters across and has a small central mound in the center. It looks as if from the impact the stuff went up and came back down. So we did get it. There's no doubt. And I think one of the bottom line messages is that this surface of the comet where we hit is very weak. It's fragile. So the crater partly healed itself. So let me turn this over to Don Brownlee and see if he can give them some data, huh? do you have the picture of the crater, Don?
We had thousands of craters. The comets, unlike any other body in the solar system, are unique because when they're in the inner part of the solar system where the Earth is, they're literally coming apart and sending tons and tons of gas and rocks and dust out into space. So last night, this spacecraft, Stardust, went through this cloud of dust and rocks coming off the comet, the second time it survived this. It actually had a dozen impacts on the front leading edge of the spacecraft here, called the Whipple bumper, that went through the front. It's a graphite cyanate honeycomb sheet that's about as thick as your finger. And a dozen of those were big enough, about almost a millimeter size, they punctured into it and went into the inside of the Whipple shield from behind. In addition to that, we have instruments on the front of the spacecraft called a dust flux monitor instrument. And this was made by a collaboration of the University of Chicago and the University of Kent in England. And they have sensors to detect these impacts. They detected 5,000 smaller particles. But one of the really interesting things about just the impact rate, and I hope we can hear the impact rate in just a second, was the nature of the impact rate. When we flew past the previous comet, Vil 2, years ago, we were stunned that instead of having a slow rise in the impact rate and then peaking out when we got closest and then dropping off, it came in sputters and starts. And everybody thought, what on earth is going on? What's going on? This is the way comets act. They don't just spew off things in a uniform way. They send it out in bursts and puffs. And even more than that, they send out clods of dirt and ice and rock that come apart. And so a good analogy of thinking of like a B-17 in World War II flying through flak. And so instead of being big, bing, 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 bing like that, it just burst of things. We had sometimes a large number of impacts in less than a tenth of a second. So it's a very dramatic environment. Do we have the audio tape on that? We have a...
They will roll it now.
Okay. If they don't, I'll simulate it. That's it. So weren't you glad you weren't on the spacecraft? And this went on and on and on. And the first impact started several minutes before the closest approach, and they continued on. But thousands of impacts, including firecracker-sized bursts. So that was really exciting. And from the comet science, it's very interesting. So there's 2 comets we've seen that behave this way. But even more, we've been to several comets now. And Comet Hartley didn't have a dust detector on it, but it took these marvelous pictures of these snow and dirt balls coming apart in space after they're emitted from the comet. So these clods come off, disintegrate, and then the spacecraft goes through them. Besides just detecting dust, we also had an instrument on the side of the spacecraft called SIDA, made by Max Planck Institute in Germany. And this measures the chemical composition of dust. And there were several dozen particles that were analyzed last night during the flyby, and this time the instrument was carefully tuned to be very sensitive to very small particles and also to measure organics. And the first spectra I saw was very exciting because it showed peaks for carbon and CN, carbon bonded to nitrogen. So anyway, it was a real thrill to do this. The whole mission was a real thrill. And it's great to use one spacecraft to go to multiple targets with the same instruments. So, that's it.
Okay, we are going to open it up to questions. In the meantime, they are trying to find the images. They were
We're also going to roll the...
And we're hoping also to have a Flickr movie of the images all together, all the images that we have so far. But in the meantime, let me go ahead and open it up to questions. We'll start in the room first if there are any questions. If not, we do have some people on the phone. Are there any questions from news media in the room? Yes, go ahead and give us your name and affiliation first.
Sure, Stan Totten with KPCC. You pointed to an image of, I'm not sure what it was, but it was a shape that you said had changed, it had eroded over time. Can you explain a little bit more what caused that shape and what caused the changes? How did that happen when we're out
Well, what
in
caused
space?
the changes, the surface of the comet is in part made of water ice. When the comet comes close to the sun, the temperature of the surface increases enough for the ices to start evaporating. That's why we see gases and dust coming from a comet. And so what you saw are places where during the last 5 years, ice has evaporated and carried with it dust into space.
It's a sublime feature.
Sorry about that.
Any other questions from news media in the room? Yes, Alicia Chang.
Alicia Chang from AP. Tim, the reason why it took so long to download the pictures, was it a result of commands that were already sent up to spacecraft before, or when you had to do the reconfiguration during the mission?
Oh, that was, yeah, the initial reconfiguration we did, that configuration was planned ahead of time. We designed that as part of the encounter. But we wanted to make sure that no matter what kind of contingencies happened during the encounter, we came out on the other side of it in a known configuration that we could support with telecom. That's why we had that particular configuration selected. Once we knew we were healthy and could support a different decoder at the station, we went ahead and asked for that because that gave us a little bit more margin on our downlink, just to make sure we had a more safety net above the signal that we had.
But the fact that it took so long for the pictures to download, was it a mistake in the commands that were sent up?
No, that initial one was driven purely by physics because it required a command to the spacecraft, and the round-trip light time is around 40 minutes. The second downlink issue that I talked about, that is a software issue that we're looking into. It was supposed to have put the 5 pre-selected images into the downlink queue first, and we don't know yet why it didn't.
But those images are on the ground.
They're all on the ground.
All right, we're going to take a question next from the phone lines. The LA Times is on the line. Amina Khan, please go ahead with your question.
Hi, thank you for taking my call. I have a couple of questions. You mentioned that the cost would be about 10% of a new discovery type mission. How much is the actual cost of this mission? The second question is related to the surface of the comet. I heard yesterday that there were some smooth areas that seemed to suggest that there had been flows along the surface. Could you talk a little about that and what might have caused that?
Okay, this is Ed Weiler from NASA. I'll take the first question. The cost of a new discovery mission to do this kind of science is in the range, counting the launch vehicle, of perhaps $300 to $500 million. This mission cost NASA exactly $29 million. So I was being conservative when I said 10%. It may be as little as 6%.
The smooth flows that you're referring to were discovered on Tempel in 2005 by Deep Impact, and they came as a surprise to Comet scientists. They have been interpreted as places where very volatile gas from below the surface has erupted, carrying with it small particles of ice and dust. And while some of this stuff leaves into space, some of it just flows downhill because the comet does have a little bit of gravity. So what is surprising about those features is that they seem to be fairly recent, and apparently they also change with time readily, because that's where we have seen the most obvious changes in the comparison between 2005 and 2011. But in short, I mean, they are apparently places where material from the subsurface is erupted onto the surface of the comet.
We'll take another question from the phone lines. We have Denise Chow with space.com. Please go ahead with your question.
Hi, thanks for taking my question. Just had a question about the deep impact crash site. When you were looking at the comparison images, I think it was maybe Dr. Larson that said that when the impactor had hit the comet, that it had all this material that sort of obscured the view in 2005. When you're looking at the images from last night, was there anything that surprised you about the impact site?
Yeah, I'll take that. Yeah, there was a surprise in the sense that you could have expected a crater that was very, very well defined. And the crater was more subdued than I think some of us thought. But it was still basically what the kind of the size that we expected. And I think the real point is that it's consistent with what we saw in 2005 with the ejecta going up and then a component coming down. And so in a way, it partly buried itself. And I think we saw that very clearly in the images you didn't see.
Trust us.
Okay, we're going to put up an image. It is the image that we do have in our broadcast system. You can tell us if it's the image you want. And just so everyone's clear, the image that they wanted will be posted to the internet no matter what, so you'll all see it. Does this one work for you?
Yeah,
great.
Okay.
Okay.
I'll talk to this.
Pete, please.
There's several things in this image I wanted to point out. One of them is that these are the two craters we're talking about. The other thing is, notice this feature that's here. If you notice over here, that feature is gone, even though many other features you can easily identify. The interesting thing is that these concentric circles represent our estimate of the crater rim, and then the inner circle is an estimate of the crater floor. You can barely see this, but there's a little lit area on that side and a dark area on the other, and that's the central mound where we think the material came down. So we think we see the crater with a sunlit rim on that side, or sunlit wall on that side, a little bit of a shadow there, and we see the mound on the floor. This is kind of what you would expect for an oblique impact at an angle of 30 degrees with a lot of material that went up and came back down.
So the picture on one side is a deep impact.
Yeah, that's the deep impact view over here, and that's the Stardust-NExT. It's about 150 meters across is what the current estimate, but stay tuned.
All right, we're going to go to another question on the phone line. Sky and Telescope, Kelly Beatty, please go ahead.
Okay, thank you very much. This is for Pete Schultz, I guess. Pete, I'm sure glad you're convinced. Is the muted nature of this crater more muted than when you would have expected, and are you anticipating finding a kind of mantling all over the comet's nucleus due to all the dust and debris that was ejected?
Well, the two questions. First is that, one of the reasons for going back to see what the crater looked like. There were some thoughts that maybe the crater would simply bury itself, or that it would sort of collapse because of its formation. In terms of the ejecta, if that was all ice, that could have sublimated away very quickly and completely by the time we got back to it. So I think when we look at this in stereo, we can see this feature, and we can see it in multiple images. And so I feel very confident that we actually did find the site.
Okay, thanks. We have one more question on the phone lines. Leo Enright from Irish Television, please go ahead.
Thanks very much. I was just wondering about this lobate feature that has been mentioned several times. Is this advancing or retreating? I think that was one of the questions that you wanted to answer.
That's an excellent question. The question is about the lobate feature we talked about. Is it eroding or increasing? At the present time, it is eroding. So it was formed at some time past and since then has been eroding.
Do we have any more questions from the news media here at JPL? No? I'm going to do one last check to see if we have any new images, if the control room can tell me. No, we are done. Those are all the images that we have. But we will be posting new images and new products to the web all day long as those become available. So please do visit www.nasa.gov. You'll find links there to all of the images from this Comet encounter. We want to thank all of you for joining us today. Good night.